Right, let's take a look now at the first of a series of gas problems. What we have is a problem where there's a gas sample and it gives you the conditions of the container that has that gas and it's asking you for how many moles. Now, anytime you have a gas sample in a container, and it's conforming to the ideal gas law conditions, which we'll always assume are there, then we can state that the pressure times the volume of the system is going to equal to the number of moles that you have times the gas constant, which is 0.082, times the temperature. So what we typically want to do is list those variables separately down the side. And the reason why you want to do that is because we want to make sure each of these variables is in the proper units. The pressure has to be in atm, the volume has to be in liters, in moles, and the temperature has to be in Kelvin. Now in this example, the pressure is at 126.6 kPa. The volume is given to us as 52.9 liters. The number of moles is in fact the unknown, and the temperature is going to be 20 degrees Celsius. So again, notice laying it out along the side here vertically and extracting the values of each of the variables, I can see very clearly where I need to go. The first one is that kPa, which is really a physics unit for pressure, that needs to be converted to ATMs. How do I do that? Well, I use first the value given, which is 126.6 kPa over 1. We're using dimensional analysis here. Now, I have a unit ratio for this, and the unit ratio says that 101.3 kPa is proportional to 1 ATM. Now, this ratio right here is based upon a whole series of interconnected ratios, such as, for example, 760 millimeters of mercury is 1 ATM. And so you're going to use those values to make these conversions. When you do this, we cancel out our kPa units, giving us our ATM. And when you do this, what you wind up with is 1.25 ATM. Now, liters looks good. We don't know the moles. 20 degrees Celsius is not going to cut it. We have to convert that to Kelvin. And to convert to Kelvin, we take the degrees in Celsius and add 273 to it. And that gives us a 293 Kelvin. So now we have all of our variables in the units that we want. And so now we just plug the values into this equation. And so now we get 1.25 ATM times a volume of 52.9 liters. That's going to equal a mole count that I do not know. My R value is 0.082, and my temperature is 293 Kelvin. When you crunch these numbers, you get 2.76 is the number of moles. And you will notice that that in fact is what I was looking for. How many moles of the gas? Now I want to again emphasize, which I did from the beginning, is in this problem we have a fixed container, and the arrangement or situation in that container is not changing. We didn't change the pressure, didn't change the temperature. All we did is had a container, and we were missing some information. And using the ideal gas law, it allows us to solve for that. Let's do another problem. Right, in this new problem, we have 135 milliliters of a rigid container. They use the statement rigid to make sure you realize that the volume is not going to be able to change. That's a fixed value. And it holds a gas sample at 27 degrees Celsius, and it has a pressure of 1.35. The question is, how many grams of carbon dioxide are in the sample? Once again, you will notice that nothing was done to the container, no temperature change or gas added. So what we have is a no change situation. And when you have a no change situation on the container, then the ideal gas law, PV equals nRT, there we go, then that rule is going to apply. And we begin by listing once again the values for the variables. And the pressure in this case is going to be 1.35 ATMs. The volume of the container is 135 milliliters. The number of moles we do not know, and the temperature is 27 degrees Celsius. Now, we cannot work with milliliters. That has to undergo a conversion to liters. And we'll do that by moving the decimal 3 places over, and so you get 0.135 liters. Now we have it in the proper units. The pressure is in the proper units, but the 27 degrees Celsius is not. We're going to have to convert that to Kelvin by adding 273 to it, and that gives us 300 degrees Kelvin. What we can now do is we can punch these values into our equation, which is 1.35 ATMs. We get a volume 0.135 liters. That's going to equal an unknown number of moles, a 0.082 gas constant, and it gives us a temperature 300 degrees Kelvin. Now, when we crunch these numbers, you get a 0.0073 equal to N, which is moles. But there's a problem. They don't want the answer in moles. They're looking for grams. So what we're going to have to do now is we're going to have to convert this mole count into grams. Now to do that, I'm going to head up over here. And what I'm going to say is carbon dioxide, CO2, you'd expect to know that. Carbon dioxide is 12 AMUs. I have one of them. Oxygen weighs 16. I have two of them. And when I crunch it out, that means I have 44 grams per mole. So now what I do is I set up my dimensional analysis. I say 0.0073 over 1. And I have 44 grams is 1 mole. I can cancel my units, and I wind up with 0.308 grams of CO2. And in fact, that is what I was looking for. So the answer to this how many grams is 0.308.